All right, today we are diving into something that sounds like it was pulled straight out of a sci-fi movie. We're talking about a completely new kind of internet, one that isn't built on simple zeros and ones, but on the truly strange, counterintuitive, and unbelievably powerful rules of quantum mechanics. But let's just start with a simple question. What if you could send a message or make a financial transaction with absolute 100% certainty that no one else could ever listen in? I don't mean because they have a bad password cracker. I mean because the fundamental laws of physics would actually make it impossible. Well, that incredible promise, that idea of perfect, unbreakable security, is the main driving force behind one of the most exciting technological frontiers right now, the quantum internet. So how in the world does this new web achieve something our current internet can only dream of? Well, it all comes down to a totally revolutionary way of thinking about security. It's done with a method called quantum key distribution, or QKD for short. And the core idea here is just amazing. If a hacker tries to peek at the quantum information as it's being sent, the very act of looking at it leaves a footprint. It actually disturbs the information, and the sender and receiver immediately know someone's on the line. It's literally like having a tripwire made out of physics. Right, so how is any of this even possible? To get our heads around that, we have to go beyond the familiar bits, the zeros and ones that power our entire digital world. The secret lies in a new, much more powerful unit of information, the qubit. You know, the classical bit of our current internet is simple, it's reliable, it's like a light switch. It's either on or it's off, a 1 or a 0. That's it. But a qubit is a whole different ballgame. It isn't limited to just one state. It can be a 0, it can be a 1, or it can be a weird blend of both, all at the exact same time. This completely mind-bending property is called superposition. It's this fundamental idea that a quantum particle doesn't have to pick a side. It can exist in this rich combination of all of its possible states at once, which means it can hold so much more information than a classical bit ever could. Probably the best way to picture this is with a simple coin. A classical bit is like a coin that's already landed on a table. It's definitely heads or it's definitely tails. A qubit, on the other hand, is like that same coin while it's still spinning in the air. It's this blur of possibility that is both heads and tails at the same time. And the act of measuring it is what forces it to finally land on one specific answer. But superposition is really only half of the magic trick. The other key ingredient is a phenomenon so bizarre that Albert Einstein himself famously called it spooky action at a distance. And this is entanglement. See, you can link two qubits together so that they share the same destiny. If you measure one and find out it's a 0, you know instantly that the other one is a 1, and vice versa. And this connection is instantaneous. It doesn't matter if they're in the same room or on opposite sides of the galaxy. And there's one more law of nature that basically acts as the ultimate security guard. It's called the no cloning theorem, and it states, very simply, that you cannot create a perfect copy of an unknown quantum state. So an eavesdropper can't just copy-paste the qubit, read the copy, and send the original on its way. The laws of physics just won't allow it. Okay, so we've got these incredible, almost magical physical principles. But how do we get from spooky physics to a functioning network that actually works? I mean, what does it take to build this thing? So here's how it all comes together in the real world. Let's say Alice sends Bob a stream of qubits. Bob receives them and measures them. Now, if a hacker, Eve, tries to intercept and measure those qubits, she can't help but change their state. Remember, you can't observe without disturbing. So later, when Alice and Bob get on a regular phone line and compare notes on just a small sample, they'll find mismatches, a dead giveaway that someone was listening. And if the line is clean, they can use the rest of the information to create a perfectly secret encryption key. And the applications of all this just get weirder and more wonderful. Entanglement also allows for something called quantum teleportation. Now, we're not talking about beaming people around, but we are talking about perfectly transferring the fragile quantum state of one particle to another distant one, essentially teleporting pure information. So building this thing requires a whole new toolkit. You need quantum nodes, which act like the routers of this new internet. You need quantum channels, which can often be existing fiber optic cables or even lasers shot through open air or to satellites. And most importantly, you need quantum repeaters to boost the signal over long distances without destroying those super delicate quantum states. But, and this is a really big but, the challenges are just immense. Quantum states are incredibly fragile. The tiniest vibration, the slightest change in temperature, can cause something called decoherence, which is where the qubit just forgets its quantum properties and collapses into a boring old 0 or 1. You can think of it like our spinning coin just wobbling and falling over before you want it to. And this constant battle against decoherence, along with signal loss and the huge task of correcting errors, is the main hurdle scientists are racing to clear right now. So, given all those major hurdles, where do we actually stand today? Is a global quantum internet some far-off dream, or is it something we might actually see in our lifetimes? Well, the progress has actually been remarkably steady. What started as just a few experiments in labs in the early 2000s grew into experimental networks that spanned entire cities, and today researchers are using satellites to do quantum key distribution over thousands of kilometers, proving that a global reach is absolutely possible. The last big step is to start connecting all these separate links into a true interconnected internet. And the payoff here goes way beyond just secure messaging. It could enable something called distributed quantum computing, linking smaller quantum computers together to solve problems that no single machine could ever dream of tackling. It could also lead to unbelievably precise sensors for things like medicine and scientific discovery, and even perfectly synchronized clocks that could revolutionize navigation and finance. So what this all really means is that we are standing at the very beginning of a brand new information age. In the same way the classical internet transformed our society in ways we could have barely predicted, the quantum internet has the potential to completely redefine what's possible in security, in computation, and maybe even in our fundamental understanding of the universe itself. Look, this isn't just about getting faster internet speeds or better video streaming. This is a fundamental shift in how we create, share, and protect information. The quantum revolution is no longer a question of if, but when. So the only real question left for us is, how is it going to change our world?